MIT researchers and colleagues have turned a magic material composed of atomically thin layers of carbon into three useful electronic devices. Normally, such devices, all key to the quantum electronics industry, are created using a variety of materials that require multiple fabrication steps. The MIT approach automatically solves a variety of problems associated with those more complicated processes. As a result, the work could usher in a new generation of quantum electronic devices for applications including quantum computing. Further, the devices can be superconducting or conduct electricity without resistance. They do so, however, through an unconventional mechanism that with further study could give new insights into the physics of superconductivity. The researchers report their results in the journal Nature Nanotechnology. The researchers say that in this work they have demonstrated that magic angle graphene is the most versatile of all superconducting materials, allowing them to realize in a single system a multitude of quantum electronic devices. Using this advanced platform, they have been able to explore for the first time novel superconducting physics that only appears in two dimensions. The new magic material is based on graphene, a single layer of carbon atoms arranged in hexagons resembling a honeycomb structure. Since the first unambiguous isolation of graphene in the year 2004, interest in this material has skyrocketed due to its unique properties. For example, it is stronger than diamond, transparent, and flexible. It also easily conducts both heat and electricity. In the year 2018, a research group made a very surprising discovery involving two layers of graphene, one placed on top of the other. Those layers, however, weren't exactly on top of each other. Rather, one was slightly rotated at a magic angle of 1.1 degrees. The resulting structure allowed the graphene to be either a superconductor or an insulator, depending on the number of electrons in the system as provided by an electric field. Essentially, the team was able to tune graphene into completely different states by changing the voltage at the turn of a knob. The overall magic material, formerly known as magic angle twisted bilayer graphene (MATBG), has generated intense interest in the research community, even inspiring a new field known as twistronics. It is also at the heart of the current work. In the year 2018, those researchers changed the voltage supplied to the magic material via a single electrode or metallic gate. In the current work, the researchers say that they introduced multiple gates to subject different areas of the material to different electric fields. Suddenly, the team was able to tune different sections of the same magic material into a plethora of electronic states, from superconducting to insulating to somewhere in between. Then, by applying gates in different configurations, they were able to reproduce all of the parts of an electronic circuit that would ordinarily be created with completely different materials. Ultimately, the team used this approach to create three different working quantum electronic devices. These devices include a Josephson junction or superconducting switch. Josephson junctions are the building blocks of the quantum bits or qubits behind superconducting quantum computers. They also have a variety of other applications, such as incorporation into devices that can make very precise measurements of magnetic fields. The team also created two related devices, a spectroscopic tunneling device and a single electron transistor, or a very sensitive device for controlling the movement of electricity, literally one electron at a time. The spectroscopic tunneling device is key to studying superconductivity, while the single electron transistor has a variety of applications, in part because of its extreme sensitivity to electric fields. All three devices benefit from being made of a single electrically tunable material. Those made conventionally of multiple materials suffer from a variety of challenges. For example, different materials may be incompatible. The work described in the Nature Nanotechnology paper paves the way for many potential future advances. For example, it could be used to create the first voltage tunable qubit from a single material, which could be applied in future quantum computers. In addition, because the new system enables more detailed studies of the enigmatic superconductivity in MATBG and is relatively easy to work with, The team is hopeful that it could allow insights into the creation of high temperature superconductors. Current superconductors can only operate at very low temperatures.